All right, we have a set of triangles that are similar. They're all right angled triangles and they're all nested inside the one big right angled triangle. But I know they're all similar because they've all got a 30-degree angle in them. They're right angled triangles with a 30-degree angle in them. I used this circle that has a 30-degree angle marked out in it so I could be a bit more accurate. But I'm going to try by measurement to figure out what sine of 30 degrees is. This means for a 30-degree angle, what is the opposite side divided by the hypotenuse side? What is that ratio going to be every time? It doesn't matter how big or small, because the triangles are all similar, then for a 30-degree angle, the opposite side divided by the hypotenuse side should always be the same. But I'm going to measure it a number of times and see if I get close to the same thing. I mean, this ruler is only calibrated every half a centimetre, so I'm only going to be so accurate. But let's see how close it gets. Starting with the small triangle, the opposite side is 13 centimetres. The hypotenuse of the small right angle triangle with 30 degrees in it is 26. So I'm saying from that measurement that always I should get 0.5 for a right angle triangle with 30 degrees in it as the angle that I'm interested in. If that's my reference angle, then the opposite of 30 degrees divided by the hypotenuse should always be 0.5. Let's just check with the next biggest triangle. That's 35 centimetres. Whoa, that was the adjacent side. I'm trying to do the sine. That's opposite on hypotenuse. 35. Let's go back and do the opposite side for this one. That is 19.5. Now, the hypotenuse for this one is 39-ish. Put that in the calculator if you need to. 19.5 on 39. 0.5. You knew that it'd be point. It's going to be 0.5 every time. But let's try the next one. 29. $58. 0.5. Let's try this really big one. 58. Can you guess what it needs to be? 116, doesn't it? But let's just check. Okay, we get up to there. And, oh, I can still measure that going backwards. 16. So by measurement, I can figure out what the ratio of the opposite to the hypotenuse should be for a particular angle. And I'm going to do that over here quickly for various other sized angles. I've drawn up some triangles to measure. And I'm going to see exactly what the values are for 10 degrees, 20, 30, well, I've done 30. 30 was 0.5. But let's figure out what it works out for 10 degrees. So I've already carefully drawn up as best I can with a protractor. I've drawn up a triangle, any right angle triangle with 10 degrees in it. It doesn't matter which one I draw because all right angle triangles with 10 degrees in it are similar. They'll all have the same ratio of the opposite to the hypotenuse. So I'll just draw one of them and measure it. Let's have a look. I get That opposite side there is 4.5. And that there is 26. 4.5 on 26. So 4.5 on 26, I get 0.173. Now this is only so accurate because look at the ruler I'm using, and of course when I drew the angles they're not going to be exact, but it's giving you an idea that if you could do it accurately you could work out what the ratio should always be for a particular one, for a particular sized angle. All right, the next one is 7.5 and the hypotenuse is 22. I'll come back and I'll work that out in a minute. The next one is the opposite side for a 40-degree one. I've got 17 and the hypotenuse is 26. I'll come back and work that out in a minute. For a 50-degree one, the opposite is 23.5 and the hypotenuse works out to be 31. And finally, for a 60-degree one, the opposite side is 37 and the hypotenuse is 43. Oops. So I can put all those into my calculator. 7.5 on 22. And I get 0.34. 17 on 26. And I get 0.6538, whatever. And then I get 23.5 on 31. And I get 0.758. And 37 on 43. And I get 0.86-ish, right? So that's from measurement, roughly what I would expect every time for every triangle that's right-angled, that has a 10 degrees in it, the opposite side divided by the hypotenuse side is 0.173. Must be. Now, fortunately, we don't have to measure it up to figure out what all these are always going to be. The calculator has a way of doing it, which we will discuss later in this topic as an extension. But just for now, you need to know that as long as your calculator is in degrees and turned on, you can just type in sine 10 equals, and it should pop that number out for you. So I'm going to check how accurate we were. Sine 10 equals. It's 0.1736. Oh yeah, we did well there. So that one's looking good. Sine of 20 degrees. Sine 20 equals 0.342. Yeah. Sine of 30. I already measured it in the triangle we did before. I got 0.5 and it is 0.5. Sine of 40, 0.642. Not perfect there, but if I'll give myself like a tick cross there, but you can see it's just the measurement tools and also the drawing of the thing in the first place that's interfered with its accuracy. Sine of 50, 0.766. That's close. Once again, I'm a little bit out, but you can see that's just the measurement techniques and instruments. And sine of 60 is 0.866. So I'll just say yes, that's good. So you can work out by measurement what they're always going to be, but it's much easier just to ask the calculator for a particular angle, what is the opposite side divided by the hypotenuse side going to be?